Today, we're gonna learn a lot about AI. Hip hooray, hip hooray. Hooray! Hello, I'm Josh Starmer, and welcome to the Uphill Conference. I'm here to talk about neural networks, where they are now, where they came from, and where they might go. So, right now, people are going totally bananas about ChatGPT. For example, StatSquatch might say something like this. What is StatQuest? Oh, by the way, if you don't already know, I have a YouTube channel called StatQuest. Anyway, so StatSquatch wants to know about it, as so do you. And the answer is, StatQuest is awesome. Bam! Now, in order to learn more about how ChatGPT works, let's learn about decoder-only transformers, which is a specific type of transformer used for ChatGPT. So we're going to talk about this state-of-the-art technology, and we're going to go through it one step at a time. Brace yourself. There's going to be a lot of addition and multiplication. You probably didn't realize this is what you're going to have to do first thing in the morning, so I'm just warning you in advance. Anyway, decoder-only transformers consist of 5 main parts. Word embedding, where we convert the input text into numbers that we can do math on. Position encoding, where we keep track of the order of the input words. Masked self-attention, where we keep the relationships or keep track of the relationships among words. And a fully connected layer and an output, where we convert the numbers back into words. Okay, anyway, in this StatQuest, we're going to show how a decoder-only transformer can take a simple input prompt, what is StatQuest, and generate a simple response. Awesome. Now, since a transformer is a type of neural network, and neural networks usually only have numbers for input values, the first thing we need to do is find a way to turn the input and output words into numbers. There are a lot of ways to convert words into numbers, but for neural networks, one of the most commonly used methods is called word embedding. Word embedding uses a relatively simple neural network that has one input for every word and symbol in the vocabulary that we want to use. In this case, we have a super simple vocabulary that allows us to input a short phrase like, what is StatQuest? And we also have an input for a potential response. Awesome. Lastly, because there's really no other response, by the way. Lastly, we have an input for the EOS symbol, which stands for end of sentence or end of sequence. Beep. Because the vocabulary can be a mix of words, word fragments, and symbols, we call each input a token. And the inputs are connected to something called an activation function. And in this example, we have 2 activation functions. This is the general architecture of any neural network, by the way. And each connection multiplies the input value by something called a weight. Hey Josh, where do those numbers come from? Great question, Squatch, and we'll answer it in just a bit. For now, let's just see how we convert the word what into numbers. First, we put a 1 into the input for what, beep, and we put zeros into all the other inputs, boop. Now we multiply the inputs by the weights on the connections to the activation functions. For example, the input for what is 1, so we multiply negative 2.38 by 1 to get negative 2.38, going to the activation function on the left. I told you this was going to be tough. And then we multiply 0.10 by 1 to get 0.10 going to the activation function on the right. In contrast, if the input value for the word is 0, then we multiply 0.61 by 0 to get 0 going to the activation function on the left. And we multiply 0.17 by 0 to get 0 going to the activation function on the right. In other words, when an input value is 0, then it only sends zeros to the activation functions. And that means is, StatQuest, awesome, and the EOS symbol all just send zeros to the activation functions. And only the weight values for what end up at the activation function because its input value is 1. So in this case, negative 2.38 goes to the activation function on the left, and 0.10 goes to the activation function on the right. In this example, the activation functions themselves are just identity functions, meaning the output values are the same as the input values. So this is pretty tough math too. In other words, if the input value or x-axis coordinate for the activation function on the left is negative 2.38, then the output value, the y-axis coordinate, will also be negative 2.38. Likewise, because the input to the activation function on the right is 0.10, the output is also 0.10. Thus, these output values, negative 2.38 and 0.10, are the numbers that represent the word what. Bam. Now, before we move on, I want to mention that all of these weights and all of the other weights we're going to talk about in this quest are determined by something called backpropagation. To get a sense of what backpropagation does, let's imagine we had this data and we wanted to fit a line to it. Backpropagation would start with a line that has a random value for the y-axis intercept, boop, and a random value for the slope, boop. And then, using an iterative process, backpropagation would change the y-axis intercept and slope one step at a time until it found the optimal values. Likewise, in the context of neural networks, each weight starts out as a random number, but when we train the transformer by getting it to predict words in known documents, backpropagation optimizes these values one step at a time and results in these final weights. Also, just to be clear, the process of optimizing the weights is also called training. Bam. Anyway, we now know how to calculate word embeddings for the first input word, what. So we'll keep track of those values in this diagram in the upper right-hand corner. Now we convert the remaining words in the prompt, is, and StatQuest into numbers. And now we've converted all the words in the prompt, what is StatQuest, into word embedding values. Bam. Okay, now that we understand how to convert words into numbers with word embedding, let's talk about keeping track of word order with position encoding. For example, if Norm said, Squatch eats pizza, then Squatch might say, yum. In contrast, if Norm said, pizza eats Squatch, then Squatch might say, yikes. So these two phrases, Squatch eats pizza and pizza eats Squatch, use the exact same words, but have very different meanings. So keeping track of word order is super important. Although there are several ways to keep track of word order, one of the most commonly used methods uses a sequence of alternating sine and cosine squiggles. Each squiggle gives us specific position values for each word's embeddings. So now let's see how we can add position encoding values to the word embeddings we created for the prompt, what is StatQuest? The first word, which in this case is what, has an x-axis coordinate all the way to the left on the green squiggle. And the position value for the first embedding is the y-axis coordinate 0. The position value for the second embedding comes from the orange squiggle. And the y-axis coordinate on the orange squiggle that corresponds to the first word is 1. Yeah. Now, to get the position values for is and StatQuest, we simply use the y-axis coordinates on the squiggles that correspond to the x-axis coordinates for the second and third tokens. Anyway, now we just do the math to get the positional encoding for all three input words. And now that we understand how to keep track of word order with position encoding, let's talk about how to keep track of the relationship among words with masked self-attention. For example, if the prompt was, "The pizza came out of the oven and it tasted good," then this word "it" could refer to pizza, or potentially it could refer to the word oven. "Josh, I've heard of good tasting pizza, but never good tasting oven." I know, Squatch. That's why it's important that the decoder-only transformer correctly associates the word "it" with pizza. The good news is that masked self-attention can help correctly associate the word "it" with the word pizza. In general terms, masked self-attention works by seeing how similar each word is to itself and all of the preceding words in the sentence. For example, masked self-attention starts by calculating the similarity between the first word, "the," and itself. Then masked self-attention calculates the similarity between pizza and itself and the preceding word, "the." And then masked self-attention just keeps calculating similarities like this, allowing each word to look at itself and the words that came before it, but not after, until it gets to the end of the input. Once the similarities are calculated, they were used to determine how to encode each word. For example, if you looked at a lot of sentences about pizza and the word "it" was more commonly associated with pizza than oven, then the similarity score for pizza will cause it to have a larger impact on how the word "it" is encoded. Bam. Anyway, now that we know the main ideas of how masked self-attention works, let's look at the details. So let's go back to our simple example where we had just added position encoding to the prompt, "What is StatQuest?" Now, since "what" is the first word in the prompt, its masked self-attention values only reflect its similarity to itself and ignore everything else. In contrast, the masked self-attention values for the second word, "is," reflect the similarity to itself and its similarity to the first word, "what." And the last word, StatQuest, takes into account its similarity with itself and everything that came before it. Now I know that "what" is the first input word, but it'll make it easier to understand how masked self-attention works if we start with the second word, "is." So let's move the position encoded "is" over a little bit to give us some room. The first thing we do to calculate the masked self-attention for the word "is" multiply its position encoded values by a pair of weights. And then we add those products together. And then we do the same thing with a different pair of weights. We do this twice because we started out with two position encoded values that represent the word "is." And after doing the math 2 times, we still have 2 values representing the word "is." Now we have 2 values to represent the word "is," and in transformer terminology, we call them query numbers. And now we're going to use the query numbers for "is" to calculate the similarities with itself and the first word, "what." And we do that by creating 2 new numbers, like we did before, to represent the word "is, and creating 2 new numbers to represent the word "what." In transformer terminology, both sets of new numbers are called key values, and we use them to calculate similarities with the query for "is." One way to calculate similarities between the query and the keys is to calculate something called a dot product. For example, in order to calculate the dot product similarity between the query and key for "is," we simply multiply each pair of numbers together and add the products together. Likewise, we can calculate the dot product similarity between the query for "is" and the key for "what" by multiplying the pairs of numbers together and adding the products together. The small similarity value for "what" relative to "is" compared to the large similarity value for "is" relative to itself tells us that is much more similar to itself than it is to the word what. That said, if you will remember the example where the word it could relate to pizza or oven, the word it should have a relatively large similarity value with respect to the word pizza, since it refers to pizza and not oven. Anyway, since is much more similar to itself than it is to the word what, then we want is to have more influence on its encoding than the word what. And we do this by first running the similarity scores through something called a softmax function. The main idea of a softmax function is that it preserves the order of the input values from low to high and translates them into numbers between 0 and 1 that add up to 1. So we can think of the output of the softmax function as a way to determine what percentage of each input word we should use to encode the word is. In this case, because is so much more similar to itself than the word what, we'll use 100% of the word is to encode is, and 0% of the word what to encode the word is. Anyway, because we want 100% of the word is to encode is, and 0% of the word what to encode is, we create two more numbers that we'll cleverly call values to represent the word what, and scale them by 0.0, and then we create two value numbers to represent the word is, and scale them by 1.0. Lastly, we add the scaled values together, and these sums, which combine separate encodings from both input words, what and is, relative to their similarity to is, are the masked self-attention values for is. Bam! Okay, now that we have the masked self-attention values for is, we can go back and calculate them for the first word, what. Remember, because what is the first word, it only needs to know how similar it is to itself. So we can get rid of most of what we did for the word is. Thank goodness. And keep the key and value numbers that we calculated for the word what. Now, just like we did before, we create a query for the word what. And now we use the query and key for what to calculate the similarity with itself and plug that into the softmax function. Lastly, we scale the value numbers for what to get the masked self-attention values for the first word what. Now we need to calculate the masked self-attention for the third word, StatQuest. So the first thing we do is calculate the query numbers for the word StatQuest. Then we calculate its key numbers. And then we bring back the keys for what and is and calculate the similarities between the query for StatQuest and the keys for StatQuest, is, and what. Now we run all three similarities into the softmax function and use the output from the softmax to tell us what percentage of each word's value numbers to use when calculating the masked self-attention for StatQuest. Now we calculate the value numbers for StatQuest and bring back the value numbers that we calculated for what and is and scale them based on the similarity scores. Lastly, we add the pairs of scaled values together to get the masked self-attention numbers for the word StatQuest. Bam! Okay, the next thing we do is take the position encoded values and add them to the self-attention values. These bypasses are called residual connections, and their sole purpose is to make it easier to train complex neural networks by allowing the masked self-attention layer to establish relationships among the input words without having to also preserve the word embedding and position encoding information. So if you're ever working on your own neural network and things aren't working very well, consider adding some residual connections. Anyways, we'll give that a small bam. Lastly, we need a way to use the encodings we have for each word in the prompt to generate the word that follows it and then generate a response. In other words, we want to use these two numbers that represent the word what to generate the word that comes after what. And we want to use these two numbers that represent the word is to generate the word that comes after is. Lastly, we want these two numbers that generate the word StatQuest to generate the word that comes after StatQuest. And that's when things start getting interesting. Hey Josh, I don't get it. Why do we want to generate the word that comes after a what when we already know the next word is? Because this is a decoder-only transformer, we need one thing that can both process the prompt and generate the output. Thus, even though we are not yet generating a response, we need to include all the parts that will do that. So now let's see what the model generates given the first word in the prompt, what. And that means taking these two values and plugging them into something called a fully connected layer, which basically behaves exactly like our word embedding layer that we started out with. This fully connected layer has one input for each value that represents the current token. So in this case, we have two inputs, and one output for each token in the vocabulary, which in this case means 5 outputs. Note, a fully connected layer is just a simple neural network with weights, numbers we multiply the inputs by, and biases, numbers we add to the sums of the products. And we've already been doing a lot of this math before. Now, when we do the math, we get 5 output values, which we run through a final softmax function to generate the next word, is. So we select the value with the highest output. If you're familiar with the concept of temperature, this is where it comes into play in this very last setting. Anyways, since the prompt was what is StatQuest, the model generated the correct word. Bam. The second word in the prompt is, and it generates boop, 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 the word what, which is not correct. Wah, wah. However, the correct word, StatQuest, was almost correctly generated, so we hope our model doesn't feel too much shame. Lastly, the word StatQuest generates beep, 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 boop, the EOS token, which is correct since we are at the end of the prompt. Bam. Now that we understand how each part of the decoder-only transformer processes the input prompt, what is StatQuest, it's time to generate a response. And that means going back to word embedding. And because we just finished encoding the prompt, we start generating the output from the EOS token. And we end up with numbers that represent the EOS token. Bam. Now let's add positional encoding. Note, the EOS token comes after the 3 tokens that represent the input. So it's in the 4th position. And since the EOS token is in the 4th position with 2 embeddings, we just add those 2 position values. And before we move on, we need to say a few more words about masked self-attention. So far, we've talked about how masked self-attention helps the decoder only keep track of how words are related within the prompt. However, it's also important to keep track of the relationships between the input sentence and the output. For example, if the input sentence was, "Don't eat the delicious looking and smelling pizza," then when generating new output, it's super important to keep track of the very first word, don't. If we focus on the other parts of the sentence and omit the don't, then we'll end up with, "Eat the delicious looking and smelling pizza." And that's not what we were told to do. And these 2 sentences have completely opposite meanings. So it's super important that when generating the output, we keep track of the significant words in the input. The nice thing is that all we have to do to add this ability to our decoder-only transformer is just include the prompt when we do masked self-attention while generating the output. So the first thing we do is calculate the query numbers for the EOS token, then calculate its key numbers, and then we bring back the key values for the prompt. What is StatQuest? And then we calculate the attention values for the EOS token. Boop, 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 Bam. Anyway, and now that we have the masked self-attention values for the EOS token, we add the residual connections and run the numbers that represent the EOS token through the fully connected layer and the softmax function. And the first word generated by our decoder-only transformer is awesome, which is totally awesome. However, even though the output is awesome, we're not done yet, because the decoder-only transformer will keep generating output until it generates the EOS token. So we plug the word we just generated, awesome, into the word embedding layer, and then we add the positional encoding using the values from the 5th position. Now we add the masked self-attention values. You guys are getting all this, right? Bam. And now that we have the masked self-attention values for awesome, we add the residual connections. And we run the numbers through the fully connected layer and the softmax. And our decoder-only transformer generates the EOS token, which means we are done generating output. Double bam. Okay, that was like the fastest ever introduction to decoder-only transformers ever presented in the entire world, and you guys were here to witness it. So fantastic. That's exciting. Okay. Now that we've seen the state of the art, that's the state of the art. That is what ChatGPT is doing underneath the hood. You lift it up, and it's just this little thing going beep, beep, boop, beep, boop. Okay, now that we've seen the state of the art in neural networks, let's go all the way back to the first half of the 20th century when neural networks were invented. So first, based on what they knew about how neurons, about what they knew about neurons in the brain, they created a network that had inputs, just like a neuron, and these inputs could be modified and merged, just like in the body of a cell, before sending an impulse, either 0 or 1, to the next neuron. For example, if we had these input values, then when we do the math, we get beep, beep, beep. Beep, boop. Negative 1.77. And negative 1.77 is this x-axis coordinate, or the input value for the activation function. And the corresponding y-axis value is 0. So the output is 0. And that corresponds to this neuron not sending a signal to a downstream neuron. In contrast, if these were the inputs, then the x-axis coordinate, or input value for the activation function, would be 2.28, and the corresponding y-axis value would be 1. So the output would be 1. And that corresponds to a signal getting sent to the next neuron. Thus, this activation function, which only outputs zeros and ones, was selected because real neurons either fire and send an impulse signal to the next cell, or they don't. Oh no, it's the dreaded terminology alert. This simple neural network is called a perceptron, because when you combine a bunch of them together, beep, beep, and connect the inputs to photoreceptors, like a cell, like the thing in a camera, you get something that can mimic how a brain processes a perceived image. And when the original design for the perceptron was first published in 1958, that's right, neural networks are old news, the author went through the trouble of showing how each part related to a biological brain. For example, the photoreceptors in the perceptron correspond to the cells in the retina. And the connections with the weights correspond to the connections in the motor cortex. Anyway, 25 years later, perceptrons were vastly improved upon by convolutional neural networks Now, this is a big mess of a diagram, but don't worry about it, because the point is, it might be easy to look at all these pieces and think they were just jumbled together and somehow it worked. However, the improvements of convolutional neural networks over perceptrons didn't come from just randomly sticking together all these pieces. Instead, convolutional neural networks were also inspired by how visual information is perceived and processed by a biological brain. Here, we see again how the author went through the trouble of showing how each part of a convolutional neural network can be related to a specific part of the brain. The point I'm trying to make is that the brain and what we know about how it works has long been a guide for making progress with artificial neural networks. In contrast, when the transformer was introduced in 2017, there wasn't any attempt to show correspondence with the brain. And for a lot of people, that was okay. In fact, a lot of people didn't even notice. The idea being, if the results are cool, then who cares? Well, before we answer that question, let me give you another example to think about. In the field of computer graphics, especially computer graphics used in video games and movies, having things look cool and drawn in a relatively short period of time are the two most important things. Nobody really cares if this mist effect is based on physics or is created with a shortcut. It looks cool and can be drawn relatively quickly, and that's all that matters. And that brings me to an old coworker of mine, Nafis bin Safar. We used to work in the basement of a hospital. Anyways, he said, "Josh, I'm out of here. I'm going to Hollywood." So he moved to LA, and he used to do computer graphics for movies. Specifically, he did the graphics for the Pirates of the Caribbean. And back then, the graphics for water were pretty good, but Nafis wanted the water to look awesome. So what did Nafis do? Nafis didn't just try random ideas that came to him. Instead, Nafis looked up and implemented the equations related to the physics of water. And the water went from looking good to looking awesome. And the water looked so good, Nafis won an Oscar. Bam! I mean, if you win an Oscar, that's about as big as the bam as you get. And we used to work in the basement. Anyways, so now let's go back to our transformer. They work pretty well, even though they don't model anything in particular. But I believe if we want neural networks to go from good to awesome, we can't just shoot in the dark and try whatever random idea strikes us. Instead, we need to get back to the brain. We need to get back to the biology so that we have a guide for what to do next. Bam. For example, I'm not just going to end on a downer like that, like wah wah. For example, I'm going to give you some ideas of what could happen next. So these are things we might be able to look forward to in the future. So let's talk about the role dopamine plays in learning. First, let's imagine we have two biological neurons. And imagine that the neuron on the left is associated with the word ball. And the neuron on the right is associated with a visual concept of a ball. Now, if Squatch says, ball, then the neuron on the left will fire. Bam. And if at roughly the same time I see a ball, then the neuron on the right will fire. Bam. The important thing to understand right now is that we needed two different inputs, the word ball and actually seeing a ball, to get both neurons to fire. Now, by firing at roughly the same time, these neurons create a potential to learn. And if during this phase, there is a potential to learn, dopamine shows up, hey guys, then these two neurons will learn that the word ball and the visual image of a ball are correlated. I'm related to that thing. I'm related to ball. Thus, the neurons have learned something new. Now, the next time Squatch says, ball, then both neurons will fire. And even though I don't see a ball, I can imagine one. Beep, 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 beep. Bam. Anyway, it might be interesting to see if someone can come up with a way to simulate the effect that dopamine has in the context of artificial neural networks. Also, this is just the tip of the iceberg in terms of stuff that happens in real brains that might be cool to implement in a neural network. Triple bam. Hooray, we made it.
That's what it is.